Hi everyone, my name is Douglas Tree. I'm an assistant professor at Brigham Young University in chemical engineering, and I'm excited to tell you a little bit today about our work using phase field models to simulate chemohydrodynamics of colloidal solutions. And so I'm going to go ahead and switch me down to the lower bit here and get going. So there are a lot of applications where you have colloidal particles with complex concentration environments. Two that I'm highlighting here are Pickering emulsions in bigels and then chemotaxis. In Pickering emulsions and bigels, you have two liquid phases that are immiscible, and you have solid surfactants or solid particles that are neutrally wetting or close to neutrally wetting that go to the interfaces between them. And this gives these types of mixtures and emulsions unique properties that make them useful for industry. Bigels making solids and Pickering emulsions making liquids. Chemotaxis is interesting both biologically and then more recently there's been a lot of attention fundamentally on studying this, and there's both passive and active versions of this as well. Passively you can have just concentration gradients that exist and particles will move in them via diffusiophoresis. There are also active versions where the particles generate a gradient on their own, which causes their motion. And I'm going to not talk about swimming here today necessarily, but about locally generated gradients. So the key thing about these systems is that they're hard to model. And I think they're hard to model fundamentally because there's a lot of phenomena that you have to try and capture. For example, you have already it's difficult to model colloidal hydrodynamics, so it's difficult to model particles in a liquid and the interactions with velocity, but there's been a lot of work on that topic. There's been a lot of progress made. But now you're adding on top of that either multiple liquid phases or concentration gradients, which also introduce surface tension. And finally, on top of that, you may have electrostatics, and so you have a lot, or electrokinetics, you have a lot of stuff going on there. And so there's a number of methods that have been introduced to be able to handle this, that approach this in different ways, and I don't have time to go over all their pros and cons, but suffice it to say that we've been looking at phase field models, which we think are an interesting and unique way of solving this that has a number of advantages that I'd like to talk about today. So the first thing I'd like to do is to introduce to you what a phase field model is. A phase field model is essentially a continuum model with transport equations, but by the addition of a free energy functional, you can then have diffuse interfaces between the phases. This means that instead of solving, say, Green's function, driven colloidal hydrodynamics, which is sort of the standard in the field. Now you're actually solving the continuum transport equation, the Navier-Stokes or the Stokes equation here, and diffusion equation, but this is augmented with this free energy functional. And really the difference is that you end up with this extra term up here, which is the sum over square gradients, which penalizes gradients, which gives you interfaces of finite width. These interfaces then lead to surface tensions and the other phenomena that are of interest here. And you're perhaps most familiar with, if you've ever heard of a phase field model, as say the Cahn-Hilliard model, and I'm showing an example of a simulation we did of a polymer solution that's undergoing phase separation. And you can see here in this spinodal decomposition that there are many, many interfaces, and so this is hard to resolve in any other way. So now, how does one go about taking this and put it in terms of colloidal particles? Well, the key idea is that if I wanted to have two liquid phases and if I wanted to make one of them solid, I could just turn the viscosity up and turn the diffusion down, and then I would end up with a solid particle. And this idea really isn't novel to us. Tanaka and Ariaki talked about this back in 2000, and they coined the term fluid particle dynamics for doing a simulation like this. And so there are a number of pros and some cons of doing fluid particle dynamics. One of the most interesting is that you sort of get for free both the velocity fields and the concentration gradients that we talked about are difficult to do. But in addition to that, you now have a different computational cost scaling. So instead of most methods where the computational cost scales with the number of colloids or the colloidal density, now it just scales with the box size. This also means that you can sort of trivially have different different colloid shapes and polydispersities because you're just creating these as initial conditions that are then frozen. The downside is that you have to resolve the interfacial length scale. So you have to resolve the sort of, not just the colloid itself, but the interface between the colloid and the liquid. But in principle, this should give us all of the hydrodynamics and wetting behavior that one would expect. So that's what we're going to test today. And so I told you that we can just turn the viscosity up. And in the previous slide, I didn't talk very much about it, but I said we could turn it up to something like 4 orders of magnitude larger than 1. And it turns out the numerical methods of that you might be a little skeptical of, but they turn out to be tractable. And so here I'm showing an example where if I don't have any, if I don't turn the viscosity, if I set it equal to 1, I get just diffusion. So even if I initialize, something I want to be a solid phase, that just quickly diffuses away. But if I take that exact same setup and now I turn the viscosity up to 4 orders of magnitude, and I turn also the diffusion coefficient down by that same 4 orders of magnitude, now the particle goes nowhere and it sits there and basically looks like a glassy solid. Okay, so I can indeed do this. So what I'd like to do for the rest of the talk is talk about what the consequences are and whether we get back the static and dynamic sort of interfacial and chemohydrodynamic behavior that one would expect. And so I'm going to start with the statics, and mostly what I'm talking about here is trying to understand the surface tension. And one of the ways that we've gone about trying to validate this is looking at the behavior between 2 liquid interfaces, or between a liquid interface between 2 immiscible liquids. So here I have 2 liquids, this orange liquid and a blue liquid, which have some interaction between them. It causes them to phase separate. In this case, we used a Flory-Huggins model with a chi parameter above 2. And then we took a particle which has no interaction between either the blue or the orange. And we can sweep where that particle is located, whether it's in the bulk of the phase or at the interface. And so if I move from the bulk to the interface, you can see that I can calculate the free energy, which I have access to because of the model, and I get a minimum of the free energy when the particle is sitting directly on the interface, which makes sense. If I then vary the size of this particle, I can plot the radius of the particle versus the free energy, and I expect that that should be proportional to the surface tension, which I can also calculate the surface tension another way and verify that this is true, and I get the behavior that I expect. Note that these calculations that I'm doing and all the calculations I'm doing in this talk are in 2 dimensions, not 3 dimensions. Our code does do 3 dimensions. It's just simpler to verify these things in 2D, and the code runs faster in that case. We can also look at these sort of frozen drops and see if they have any type of interaction between them. And it turns out that they do. If you try and shove them together, you get the free energy that goes up as the particles start to touch. And this is because you're deforming the interfaces, and that causes a surface tension to go up, and they don't like that being deformed, and so that's a repulsion between them, which is great. So they're even acting a little bit like solids that repel. Okay, so now we want to turn our attention to the thing that I talked about in the title, which is what about the dynamic interfacial forces? And so the first thing I'm going to show here is a particle moving in a solute gradient, which is classic diffusiophoresis. Okay, and you can see here it's a little bit subtle, so I'll keep playing it because I couldn't get this to loop. But basically the particle starts to the left and moves to the right, and you can see that the gradient moves from left to right. So we get diffusiophoretic motion along that gradient. And we'd like to be a little more quantitative about it rather than just say, do we get that motion? So we looked up theories of diffusiophoresis and compared. And basically the diffusiophoretic velocity should be proportional to the concentration gradient, which is one expects. But there's also these terms that have to do with the boundary layer thickness and KT over the viscosity. And so it turns out that we can compute these boundary layer thickness from other simple simulations, and I don't have time to go into the details, but if you do that, we see pretty good agreement between our simulations and the theory. And so we think that we're getting a diffusiophoresis that makes sense according to theory. Okay. The other thing that's interesting is now that we believe that we have diffusiophoresis, we can start to play games by looking at active particles. Okay, and so what I have here is a Janus particle, and you're only seeing the solute concentration in the video, but I have a Janus particle that has now two components, both of which are frozen, one of which will react with a reactive a species in the solution and turn it into the solute that is then interacts with that particle. And when I do that, you can see now that a gradient develops around the particle, and without imposing an external gradient, I get a particle that moves as an active particle. And note that this isn't something, I haven't given any velocity to this particle to begin with. It's only the rise of this concentration gradient that makes this particle move. Okay, so I'm about out of time, but we think that these phase field models, or the fluid particle dynamics, as Tanaka calls them, can be used to simulate colloids alongside a lot of interesting cases where you have complex concentration gradients. And in particular, there are unique strengths and weaknesses of this method relative to other methods. So it's easy to calculate concentration gradients. It's easy to do polydispersity. It's easy to do high density. It's relatively difficult to do really large systems spatially, but we're working on expanding the methods to be able to handle those systems. So what we've seen so far is that, is that fluid particle dynamics correctly models both the static interfacial energies and dynamic interfacial flows. And you can see down here sort of a plethora of examples that we have. In this case is a spinel decomposition, and this thing started running without me, so you can see it better at the beginning, with particles in there. This case is a shear flow with multiple liquid phases and particles in it. And here's a complex gradient without different phases where particles move along the gradient in a diffusiophoretic motion, but the solute's also diffusing in time, and so you have an interaction between those. So with that, I'd like to thank you for your attention, and would welcome any questions via the means that are available.